purpose of this project, Agua para Siempre, Water for Always, is for the reconstruction of the water distribution system located in Tejeras, Honduras. The project goals include integrating local knowledge and organizational structure into designing a culturally appropriate potable water system with 100% environmental and economic sustainability, implementing a water distribution system that provides clean water to 100% of homes in Tejeras, educating the community of Tejeras and Ajasted on system management and maintenance issues, ensuring water security for future generations of Hondurans, and provide an invaluable learning experience for students, promoting globally aware and internationally responsible engineers.
This is ground control to Major Tom. You've really made the grade.
Village in Honduras with a fast-growing population of approximately 700 residents. Honduras is located in Central America, and Tejeras is located south of Pico Bonito National Park, 120 kilometers south of the major coastal city of Las Vegas. Tejeras' economy relies on agriculture, construction, and cleaning services. The community has a water board called La Junta de Agua that works to make decisions on the community's water resources and infrastructure. Each household in the community pays a fee of $1 a month for maintenance and operation of their system. Tejeras receives their water from a river a few miles up the mountain from the village. The community is located on a mountain slope with an elevation difference of approximately 570 feet between the river source and the last node along the distribution system. The system is gravity fed and requires no pump. A chlorination tank is located at the top of the community which feeds into the water distribution system. Currently, the pipe network in Tejeras provides water to about 110 households with a total water demand of 82 gallons per minute. Due to lack of engineering expertise, the distribution line fails to provide a sufficient amount of water to the expanding community. As seen in the picture on the left, a great portion of Tejeras' 4 miles of distribution pipe is exposed to the atmosphere. Typically, PVC pipes are laid underground for protection from the sun and forces directly impacting the pipe from above ground traffic, which can rupture the pipe. Thus, the exposed pipe has led to cracks and leaks that prevent residents from receiving water much of the time. The project scope includes a water study including hydraulic analysis, pipe network redesign, construction plan and schedule, a training program for community including a PVC pipe network installation guide, and an environmental impact report.
Rain, don't go away.
In order to determine the proper techniques to build the pipe network for the Honduran community, an analysis of the local conditions were analyzed to deter any gross miscalculations and misjudgments. The average rainfall during the months of May through August is about 3 to 9 inches. There is about 10 to 18 days of precipitation per month and a high temperature of about 80 degrees Fahrenheit. Tejeras' colder seasons happen during the months of January to March, when the team would most likely implement the pipe system, with an average temperature of 54 degrees Fahrenheit. Its warmest days happen around April all through July, average temperatures of about 87 degrees Fahrenheit. From these values, we can anticipate a high soil saturation value and a steady water inflow into the system with continual precipitation year-round. We estimate that the soil composition is composed of acrosoil. Acrosoil soil consists mainly of clay particles and is located in humid tropical areas. It is usually a low saturation value, and from this analysis, the proper pipe laying techniques may be determined.
To assist in the analysis of the existing system, Team Tejeras utilized WaterGems, which is a software program used for modeling all types of water distribution systems. The program takes into account the physical properties of the system to calculate volumetric flow rates, hydraulic velocity inside pipes, pressure within junctions, volume of tanks, and so much more. Our model is based off the distribution system sent to us by Ajasted, overlaid a map of the community extracted from Google Earth Pro, and a demand of 0.73 gallons per minute designated for each household. The current system has too many pipe contractions and expansions. There is no uniformity. Also, certain sections of the system have flows that move uphill for extended lengths. When adding to the system, several of the pipes were duct taped. All of these lead to huge energy losses. This is the area where the bulk of the houses are. All of them have negative pressures. Low readings can be due to leaks, clogs, lack of hydraulic energy, and so on. Replacing the piping is the best option. The proposed system is more consistent to decrease these minor one-time losses. It will have primary lines of 2 inch, secondary lines of 1.5 inch, and tertiary lines of 1 inch. Additional pipes were added to the system to create loops in order to increase the pull on the water and make sure it flows downhill. Adding more loops will also help for future plans. It allows for smaller areas to be sectioned off so a minimal number of people will be without water during these processes. Ball valves were added at the beginning of the primary and secondary lines to make this a possibility. Loops will require valves at the end as well in order to completely isolate the section. Arrows on the model mark where the new pipes are. The pipe on the right loops 2 secondary lines to keep the flow progressing downhill. One of these secondary lines originally ran completely uphill. The pipe in the bottom left of the model is incorporated to spread the pressure from one of the main lines that barely has any branching pipes. This primary line runs down the entire road, building up pressure. The new pipe connects this main line to another main line that has the bulk of the distribution lines linked to it. There's no longer any negative pressures, and they're high enough to even add more lines.
The future is coming on, it's coming on.
Recommendations for future plans are to build downhill. Use gravity to your advantage, otherwise a pipe will be necessary to increase hydraulic energy amongst the system, which leads us to our next point: buy a pump. It may increase the energy in the system, but this option adds operation and maintenance costs, so it is not ideal. However, it is an option. Also, add another pipe from the reservoir. The reservoir has an overflow of about 100 gallons per minute. This is already being wasted, so why not put it to use? Finally, the community is continually growing, and within 10 years the pipe may need replacing. 3-inch diameter pipes used for the main trunk lines can increase the amount of flow through the system.
The pipeline distribution system will fully replace the current water distribution system. Overall, there is about 4 miles of pipeline determined to be trenched and placed underground. The whole of the distribution system is divided into 16 sections, separated by accessibility, and allows for the breakdown of the entire pipe network. Many of the main lines are controlled by a valve which allows for the construction of varying sections at different times, accommodating for weather and other disturbances. The trenches will be constructed next to the current distribution system and should be near completion before that specific section is offline. This allows for the minimal amount of time that terminations will be without water. A pipelining manual was created that goes into detail about the proper pipelining technique. Following that manual, operations and maintenance manual was developed that will assist in the upkeep of the system.
I see trees of green, red roses too.
The meaning of environmental impact report is a document usually required by the United States government to assure the proposed action, in this case pipe laying, does not have significant environmental impact or affect the quality of life of the community. Although this is not required by the Honduran government, Team Tejeras prepared a report for the interest of providing the community valuable information regarding public health, conservation of the community's resources, and other considerations made towards rebuilding the water distribution system. The EIR is an essential tool that helps in the decision-making process and increase the range of alternatives to minimize impacts on the environment and our community. This document lists possible social, environmental, and economic factors that may be affected. Two main ones are public health and wildlife and vegetation. Public health covers two main areas. These are pipe material and water distribution. The historical pipeline performance is also an important factor. Learning the conditions of the old pipe and the problems related to this will allow us to make decisions for the new type of material for the new pipe installed. The purpose of reconstructing the pipeline is not only to ensure water to each household, but to provide clean water to each of the community members. A rusty pipeline will not provide clean water and may cause serious illness to the population. Therefore, The old pipeline will be removed and new pipes will be installed. The material of the pipelines is important to ensure quality for an extended period of time before it needs to be replaced. Another second important area is wildlife and vegetation. There are very sensitive animals inhabiting the area that can easily get disturbed by noise or construction in general. There are three key elements for successful implementation, and this consists of education and outreach, communication with construction management leaders, and proper use of user manuals to maintain pipeline and best conditions as possible.
Drawing from the construction plan of the water distribution system, a rough construction schedule was formulated to estimate the time and consequently the budget of the project. The schedule takes place in one-day increments, beginning with overall inspection of the current system, acquisition of the materials, and training of the skilled and unskilled workers. The valve boxes are then created and valves implemented before the large-scale construction process. From there, each section is trenched and placed according to the construction plan. After completion of the excavation and placement of the pipe in accordance with the installation guide for the final system is inspected for errors and proper placement techniques, and any necessary changes are implemented.
Here are several images of the materials that will be used. The entire system will be made out of PVC. PVC pipes, bends, and valves help save energy, conserve water, provide a higher quality of water, save money, and have proven longevity in service. Ball valves are chosen because they're easy to use and they are used for isolation and shut-off within water systems. Concrete is needed to make the boxes for the valves. The hardware listed is pickaxes and shovels for digging the trench, pipe cutters used to cut the PVC pipe, and a concrete saw to shape the valve boxes. The pipes in the existing system are not properly put together. Therefore, we need to use primer, glue, and sealant to ensure that the system does not have too many losses. Tarps will be used to cover PVC during construction. Long solar exposure ruins PVC. The entire budget will cost $24,300.